we are going to talk about Lucene internals. It's something that I found very interesting, so I'm going to try to make it interesting for you too. About me, so my name is Adrien. I come from France. I'm a Lucene and Sora committer, and I work at Elasticsearch. And one way you can see that I'm interested in the Lucene internals is that I've changed a lot of the index file formats over the last month. So I started with stored field, but I ended up working with the stored field format, the term vectors format, and doc values as well. And so I'll try to give you insight into the way it works with Lucene. So one question maybe you had before coming to this talk is, why should I learn about Lucene internals? So you may think that if you need to learn about the internals of something, it means that the API is not good enough. But actually, there are very good reasons to learn about Lucene internals. The first good reason is to know the cost of the APIs. So it's very important to know the cost of each API if you want to best use them and to build blazing fast search applications. There are a few things that you should never do with Lucene, especially you should never commit all the time. So doing a Lucene commit every time you add a document is the best way to have a very, very slow indexing with Lucene. There is another question that people have, which is, for example, when should I use stored fields and doc values? Because Lucene provides these two options in order to access field values. So when should I use which one? This is a question you may have when you start using Lucene. And finally, it's very important to know the cost of the APIs, because the fact that you can do something with Lucene doesn't mean that Lucene is the right tool to do it. So hopefully the fact that you know about Lucene internals will help you better decide whether or not you should use Lucene. Another reason why knowing about Lucene internals can be interesting is to understand the index size. So very often on the mailing list, we have people who come and ask, so I just deleted like 20% of my documents, so how come that no space at all has been reclaimed? So does deletion work at all? So what's the issue? And actually, this is very easy to understand if you know the way Lucene works. And finally, I think Lucene internals are very interesting, so I'll try to share things I learned to know in the last few years about it. So coming back to Lucene, Lucene is all about indexing. So what is indexing? The main point of indexing is to make data fast to search. So how can we do that? There are several things that you can do. Something you should not be afraid of is to duplicate data if it helps. So this is something that Lucene is doing all the time, duplicating data, so that you can access it very quickly, no matter what your access pattern is. And in order to make data fast to search, you need to decide on how to index your data based on your queries, not based on your document. Meaning that if you want to make data fast to search, putting it into Lucene index is not good enough. You also need to think about the way to index data in Lucene. So most of the time, Lucene does what it can in order to trade update speed for search speed. So comparing Lucene, I mean, an alternative to Lucene could be to use grep in order to find matches, for example, in a file that contains lines that you are interested to find. But if you are going to run many queries against a single dataset, indexing this dataset into Lucene is probably going to be a better option. But then there are also other questions that you should ask yourself before doing that, which is, what kind of queries should I do? If you build a Lucene index and keep only running prefix queries on this Lucene index, it means that you are completely misusing Lucene, because you are indexing tokens and querying on prefixes, which is not what you should do. Instead, you should index prefixes so that at search time you can run simple term queries which are super fast to run. Another example is phrase queries versus singles. So if you keep running phrase queries on your Lucene index, Again, you may be misusing a bit your Lucene index, and a better option could be to use shingles. So shingles are basically concatenations of terms, and again, like grams, this allows you to use simple term queries instead of complex phrase queries in order to find documents in your Lucene index. So as I said, indexing is about trading update speed for search speed, but most of the time indexing is much faster than what you think. So for example, we have a Lucene commuter whose name is Mike McCandless, who runs daily benchmark of Lucene, and the last time I checked, the update rate for 4 kilobyte documents extracted from Wikipedia was 220 gigabytes per hour, which is, in most use cases, a very good indexing rate. So we'll try to build a Lucene index from the ground up. So how can it work? So one option to build a Lucene index could be to use a hash table in order to map terms to documents. Hopefully this doesn't work for all queries, especially if you want to run things like prefix queries or range queries. You need your index to be sorted. This is why most of the time index structures are using trees. So if it is in memory, this can be a simple tree map, like in Java. And when it's on disk, it's usually a B3, like in common SQL databases, like MySQL or MongoDB, which is using B3 as well. And here is what it could look like. So in this example, we are indexing the content of 2 books. So we have Lucene in Action and a book about databases. And we have 5 keywords. So we have data, Lucene, index, SQL, and term. So SQL has a single pointer, which is in green because it's contained in the database book. But for example, if you look at the index term, it has an linked list with 2 elements. The first one is Lucene in Action because index is contained in the Lucene in Action book. But it also points to a single entry, which is in green, meaning it is a pointer to databases, because the index term is contained into these 2 words, into these 2 books. So this is the way most indexes work in the world, but Lucene doesn't work this way. So here we just tried to use a tree in order to have our content sorted, but there is another way to do that. It's to use arrays. So let's use arrays and keep them sorted. So once again, we have our 2 documents, which we are putting into an array. So we are not sorting them. We are just putting them into an array. And we are using the index of the array as an identifier for these documents. So in that example, Lucene in Action gets doc ID 0, while databases get 1 as a doc ID. And then we are going to use 2 parallel arrays for terms and what we call postings, which are document identifiers that contain this term. So the content of the index is exactly the same as in the previous slide, meaning that we have 5 terms, data, index, Lucene, term, and SQL. And on the right, we have the identifiers of the documents that contain this term. So both on the right and on the left, the first column is not stored in the index. It's just the index in the arrays. And this is actually how Lucene indexes work. So in Lucene terminology, what we are seeing here is a segment. In the document, the index in the arrays of documents is what we call the doc ID. Then we have the document. And in the inverted index, we have the index, which is the term ordinal, the terms which are contained in what we call the terms dictionary, and we have the posting list. So this is a Lucene index. So this architecture may sound a bit strange because basically we have exactly the same content as before, but we just lost something which is very important, is that this data structure is not updatable. And in the next slide, I'm going to try to explain why actually it's a very good idea to use this architecture. And so let's start. So this is immutable, meaning that if you want to add a new document which has a term that could be, for example between index and Lucene, inserting data into an existing array is very costly, so this is not something we want to do. So the way to add data into Lucene is to write a new segment. So for example, let's imagine that we only had an index that stored Lucene in action. So we have 4 terms, and they all point to document 0. And we want to add, we want to index databases into this index. What we are going to do is that we are just going to create a new segment. So again, this document has 3 terms, data, index, and SQL. And this is how you add data into Lucene. So when you want to search, the only thing you need to do is to go over all segments which are contained in your index and to concatenate the results for every segment. So after doing a lot of update, you may end up with a very high number of of segments in your index, and this is bad for search speed. So something that Lucene keeps doing in the background is running background merges. So background merges, merges in general are very simple on the Lucene index. So let's imagine that we want to merge the 2 segments on the left. It will end up with a segment on the right, and the way it works is that you are going to take the second segment, you are going to increment the doc IDs by the number of documents that are contained in the first segment, and then we are only going to merge the terms dictionary and the posting list. So data is contained in both segments. So there is a single entry for data in the new segment, and it contains the union of the posting list for these 2 segments. So in the end, merging is not that expensive because all we had to do is to concatenate documents. So as you can see, we just had to concatenate data for Lucene action and databases to build the stored field of our new segments. And to merge the term dictionary, all we had to do is to merge 2 sorted lists. So this means that in the end, merging segment and segment again is exactly like running a merge sort on the terms dictionary. So this is something which is quite efficient. Now, how do we do deletions? So the way deletion works is that in parallel to your documents, we are going to store a bit set where a value of 1 means that your document is live in the index, whereas a value of 0 means that your document is deleted. So for example, let's say that we have the index that we just created by merging 2 segments after adding 2 documents. And if you want to delete the databases book, all you need to do is to turn off the bit which is associated with databases. So in this example, databases has been removed, and actually when Lucene will run search, it will read the posting list, but it will remove dynamically at search time from the posting list documents which are deleted according to the live docs. By the way, the way space is reclaimed in Lucene is that when you run a merge on a segment which has deleted documents are not going to be part of the new segment. So if you remember the question that I mentioned that we get sometimes on the mailing list of the user who was surprised that space was not reclaimed after he deleted 20% of his documents, the reason is that space will be reclaimed on the next merges that will contain the segments where the deletions happened. This is how space gets reclaimed in Lucene, and this is the reason why there is a small delay between when you delete documents and when the space is reclaimed. So, still, it may sound, a lot of overhead because at the beginning we had a very simple index which supported updates in place, and it looks weird to try to build something based on immutable data that makes updates much slower, because every time you need to add a document, you need to write a new segment. So let's try to draw the advantages of this new indexing architecture. So one big disadvantage is that updates require writing new segments. This means that if you want each write to be visible to your index reader, every time you need to write a new segment. This is going to be very costly, and this is something that B-trees indexes, for example, handle much more efficiently. However, this has a lot of advantages. So Lucene has the ability to buffer documents into memory in order to write all of them in a single segment at once. And one important thing in that case is that all writes are going to be sequential. This is something which is very important for indexing speed. So, as I said, segments are never modified in place. So this is actually only partially true because this is only true for deleted documents, and very soon, thanks to Shy, to numeric doc values. But the rest of the data, like the terms dictionary, the stored fields, can never be modified in place. And this is good because when you store data on disk, this means that it's going to be more file system cache friendly, because once something is cached into the file system cache, it never needs to be invalidated, because it's always going to be relevant, because you are never going to modify the on-disk data structure that were used to load this data into memory into the file system cache. Another advantage of having immutable data that you may know if you come from some functional programming languages is that multithreading and concurrency is much easier to do. So especially whenever you run search in Lucene, Lucene is going to be able to use all your CPUs because there is absolutely no lock when you run search on a Lucene index, even if you are using updates in parallel. Searching is completely lock-free in Lucene. There is no lock involved. So another good point, which was already the case, but it's still good to mention, is that terms are deduplicated. This means that if you have a very high number of high-frequency terms, we are going to save space because we are going to store them only once in the index. Documents are uniquely identified by an ordinal. So I said that one way to make data fast to search is to duplicate data depending on the access pattern that you are going to apply on the access pattern that you are going to use. And the fact that data is immutable and that documents are uniquely identified by ordinals is very useful for cross-API communication, and we'll get into this a bit later. Another very important advantage of Lucene compared to traditional databases is something that people don't always realize, but Lucene is able to use several indexes at the same time. Again, we'll get into it in the next slide. And to finish with, terms are uniquely identified by an ordinal as well. This is important for two things. This is important for sorting, because this means that when you are going to sort your matching document, Lucene is not going to compare the bytes of your terms, it's going to compare the ordinals. And as you may know, comparing longs is much faster than comparing strings, even if they're in memory. And it's important for faceting as well, and we'll get into this later. So, a very important point I mentioned, Lucene can use several indexes, many databases can't. So, why is that? The way Lucene stored posting list on disk is the following. So here, let's imagine we have two posting lists for red and shoe. If you want to compute the intersection over the two posting lists, Lucene is going to be able to skip over some documents. So, for example, let's say that we are currently at this position in the index, in document 20, and we want to get to the next document. On this posting list, we find that the next document is 30, meaning that on this posting list, we can skip over a large number of documents in order to go to the next document, which is equal or greater than 30. This means that we didn't even have to visit these two documents. So in this example, the gains may seem not that big, but if you are thinking about very sparse posting lists that still contain tens of thousands of documents, this is a huge performance benefit. And again, something I didn't mention is that the way the posting lists are stored doesn't depend on which field they are indexed in. This means that this is going to work if red and shoe are two terms of the same field, but this is going to work in the exact same manner if these two terms are stored in different fields. And this is something that most databases can do, and the only thing that they do in that case is that they pick the most selective index, and they just forget about the indexes they have on the other field that you are querying on. So we just covered search, but Lucene has many more APIs. In particular, you can use term vectors, norms, numeric, binary, sorted and sorted set doc values. We are going to see the way they are stored in a Lucene index. Sorry. So what are term vectors? So basically, term vectors are per document inverted indices. So let's say we have the following inverted index on the left. How would term vectors look like? So basically, term vectors are actually like the inverted indices we had when we wrote a new segment because we needed to add data into our index. So basically, the kind of things that term vectors can tell you is, for example, the unique set of terms which are contained in your document, as well as their term frequencies and their offsets. This is something that the inverted index can do, and this is one good reason to use term vectors. So the perfect use case for term vectors are more like these queries, because it means that you are going to be able to intersect very efficiently the terms dictionary of a single document with, for example, the term dictionary of an index where you are interested in getting similar documents. Another use case for term vector is highlighting. So as you may know in Lucene, there is a fast vector highlighter. You may know it as well if you are using Thor or Elasticsearch. And this fast vector highlighter actually uses term vectors in order to do the highlighting. So now we have doc values. So let's start with the simple one, which are numeric and binary doc values. So they are very simple. They only store, so in the case of numeric doc values, a number per document, and in the case of binary doc values, a byte array per document. So they are stored in parallel of the stored field. And for example, a way to store them in memory could be to use a simple long array for numeric doc values and an array of byte arrays for the binary doc values. So for example, here we are associating a numeric doc value of 1 with the document for the databases book. So these two fields are single valued. This is how we can have such simple storage. So when you have multi-valued fields, something you can do, but which has not been built for the same use cases, are sorted set doc values. So sorted set doc values are a bit like the inverted index, but the other way is that we still have a terms dictionary, but instead of mapping terms to document, we are going to map documents to terms. So the way it works is that for every document, we are going to store the ordinals of the terms which are associated with this document, and then we are going to have a terms dictionary which is going to map the ordinals of the term to their actual value. So in this example, we have, for example, Lucene action, which is associated with sorted set doc values terms 1 and 2, which are Java and search, because Lucene in action is talking about search implemented in Java. We could do the same for the other documents. So what is it useful for? So, oh, sorry, I didn't mention. Sorted doc values are exactly like sorted set of values, except that you can only have a single term associated with a document. So sorted doc values are useful for sorting. This is what will allow you to compare ordinals, which are numbers instead of byte arrays or strings. And sorted set doc values are used for faceting. So let's try to re-implement faceting on top of Lucene. So first, what is faceting? So faceting, very simply, consists in computing counts per unique value of a term. So let's imagine that you are a web shop and you are selling shoes, for example. Maybe you would like to compute counts according to the size of the shoes that you are selling. So this is something that faceting allows you to do. And the powerful thing about faceting is that it's going to be able to compute it very efficiently per query. It doesn't only work on the whole dataset, it's something that you will be able to compute very efficiently per query, no matter the documents that are going to be matched. So let's try to implement it. a very first naive solution would be to go through the matching document, and for every matching document, to get the list of ordinals of terms which are associated with it, and for every document, for every ordinal, to get the value, and to put them in a hash table in order to aggregate the count. This would work. So, and the cost of this naive solution is that you are going to do something which is linear in the number of matching documents for ordinal lookups, and again ordinal in the number of matching documents for value lookups. So let's try to do something better now. So this time we are still going to use a hash table to aggregate counts, but we are going to map ordinal to counts instead of values. So this is a benefit because this means that for every document, instead of getting first the ordinals and then the values, we are only going to get the ordinals, and we are going to resolve values in the end. This means that in the hash table, we are going to do the collection based on ordinals, and when collection of the index is finished, we are going to replace the ordinals with their value. So the benefit is that this time, we are still doing a number of ordinal lookups which is linear in the number of matching documents in your index, but we are going to do many fewer value lookups, which is only linear in the number of unique values. So for example, if you have only, maybe, I don't know, you have 1 billion different shoes that you are selling in your online shop, but you only have 10 possible sizes, this is going to be a huge performance speedup. And something else to note is that the hash table that we are using to map ordinals to counts can actually be replaced by an array, where the key, where you use the index of the array as a key and the value as a value. And this is going to be much more efficient than a hash table because we don't have to do hashing anymore, and we don't have to do collision resolution. So this is why faceting is so fast with Lucene, and this is why Lucene-based applications really shine at analytics, because they are going to do this kind of computation very efficiently. Okay, so how can you use these APIs? So these APIs are actually not only internal to Lucene. These are APIs that you can use yourself. And everything is Lucene is based on these APIs. This means that search, you could re-implement search fully based on these APIs. So how can you access them? So the inverted index is accessible through atomic reader.fields. Stored fields are index reader.document. Livedocs are atomic reader.livedocs. Term vectors are index reader.termvectors. And finally, for doc values and norms, you have atomic reader.get norms value, get numeric doc values, get binary doc values, get sorted doc values, and get sorted set doc values. So all these APIs are publicly available. And if you would like to, for example, to re-implement search in a slightly different way than Lucene does, it is something that you can do because all these APIs are public and you can use them. So let's wrap up what we just said about a Lucene index. So if you counted, actually, we can duplicate data up to 4 times. So once for stored fields, once for the inverted index, once for doc values, and once for term vectors. But actually, this is not a waste of space at all because all these APIs have different access patterns, and Lucene is storing data in a way that is going to be fast to access for these APIs. This means, for example, if we didn't have the inverted index, we would need to go through every stored field in order to find matches, and this would be super slow. This is why it is really useful to duplicate data. And it is very easy to manage in the Lucene architecture because everything is immutable. This means that it is much simpler to keep data in sync, even though it's stored, for example, in different files. Let's go back to the questions I asked at the beginning about stored field versus doc values. So this is a question we get quite often on the mailing list in different forms. Sometimes it's not phrased this way, but the underlying question is this one. So when should you use doc values versus stored field? Because both APIs are very similar. Actually, for stored fields, you would first get a document and this gives you a map which maps field name to field values, so you can get the value. And doc values are the opposite, meaning that first you tell the index reader, I want to get doc values for this field, and then you can tell the doc values object, please give me the doc value for this document. So these APIs are a bit similar, and the way they are stored on disk are the following. So for stored field, we are going to store all field values sequentially. So for example, we would have value for field A of document 0, followed by value of field B for document 0, followed by values of field C for document 0, etc. for document 1, for document 2. Whereas for doc values, it's as if they were stored in different files and sequentially, but per field. So when to use stored field and doc values? A rule of thumb is that you should use stored field when you want to get many field values, but for a few documents, and you should use a few and doc values, sorry, when you want to get a few field values, a few field values, but for many documents. What is the reason? The reason is that for stored field, for example, let's say that you want to get all field values for document 1. You are going to do only at most one disk seek. For doc values, you may, for example, here we have 3 fields. You are going to do up to 3 disk seeks. So definitely, if you want to get values for, a few documents, stored fields are going to be more efficient. On the other way, if you are going to use, let's say, numeric doc values in order to modify the score which is computed by Lucene, a better option would be to use doc values. So why is that? For example, let's say that you are going to use only field A and field B for scoring and not field C. With stored field, because of the way disk work, so just take some minutes to talk about it. But when you read disk on your operating system, even if you only need to read 1 byte, your operating system is actually going to read 4 kilobytes and to load it into the file system cache. So this means that, for example, if you want to load the value of field A of document 0, it is actually going to read the value of field C as well. And this is not something we want to happen because it's going to pollute the file system cache, which is a very important performance factor for the Lucene index. And this is something which is not going to happen with doc values. For example, if you want to load, let's say, values for field A and document 0, we are not going to load into memory data which is relevant to field B or field C. We are only going to load into memory data which is relevant to field A, and this is why you should use doc values when you want to get a few field values but for many documents. So typically, if you are doing scoring or faceting or sorting, you want to use doc values. Okay, so that's it about the basics of the Lucene architecture. I'm now going to dive into the file format. So, some important rules that we apply when we write new index file format is that we want to save file handles. Definitely, you don't want to write one file per field or per document. So, for example, let's say that you want to write a stored field format. Some people, such as Michael, would like to store every document in a different file. Although this might work in some cases where you don't have too many documents or your documents are very big, most of the time it doesn't make sense because for performance reasons, you want to keep your files open all the time and not keep on closing them and reopening them, which is very costly. You want to keep them open, so you need to use as few files as possible. This is why Lucene is a bit worried about file handles and tries to store data into as few files as possible. Actually, we even have an optimization for flush segments, is that whenever you, by default only, whenever you are going to flush segment to disk, it's going to write into what we call a compound file, which is actually a file which is a directory for other files. So the reason why we do it is to save file handles. However, bigger segments are going to have their own files on the file system. Another rule is to avoid disk stick as much as possible. Especially on slow disk, such as spinning disk, disk stick can take a very long amount of time, so it's very common that a disk stick on a spinning disk takes 10 milliseconds, and this is something that we want to avoid. But on the other hand, we shouldn't ignore the faceting cache, which is handled at the operating system level, and it's going to cache in a least recently used fashion the last regions of the disk that we read in 4K blocks, as I was describing a bit earlier. So actually, doing random access in small files can be okay. And last but not least, whenever possible, we would like to apply some light compression, which compresses enough in order to make data smaller on disk, so that it saves some I/O and can make the indexes smaller, so that the file system cache can do a better job at caching data into memory. But on the other hand, we don't want compression to be too heavyweight, otherwise the bottleneck won't be the disk anymore, but it's going to be your CPU. So this is something that we try to do in the different files which are stored in your Lucene indices. So the way we store data on disk actually depends on codecs. So codecs are a new feature. I mean, it's not new anymore because it was introduced in Lucene 4.0, which is 1 year old now, but it's still a pretty new feature, as a lot of people are still running Lucene 3.6, for example, indices. And something that changed a lot with codecs is that the file formats are actually dependent on the codec. Tomorrow, for example, you can write a new codec for Lucene, which will allow you to store data in a completely different manner, although it's kind of an expert setting. In Lucene, there is a default codec, where we try to do some good trade-offs between speed and memory. And in general, what we try to do is that we try to put as many data as possible to disk, but we try to keep it fast enough. So a very good information to you is that if you want your search to be super fast, the way to do it is not to use a RAM directory, which, if you don't know, is a custom, it's a different Lucene directory implementation that stores data in memory. This is not the way you should make your search faster. The way to make your search faster is to use custom postings format and doc values format that will load part the totality of the data, but only for doc values and posting list into memory. So in particular, if you want to have very fast primary key lookups, you should definitely consider using memory posting format. And if you have workloads that rely a lot on doc values in order, for example, to compute custom scores, I definitely recommend using memory doc values format, so that your queries are going to be much faster. So I'm not going to give too many details about the index file format. If you would like to get details about them, you can read. We try to write them in the Java docs, so that if you go to that page, you are going to have links to the different files that we store in the Lucene index, and you are going to have a description of the file format we are using in the default codec. Now, so starting from now, I'm only going to describe what happens with the default codec, which is the one that probably 99% of people are running in production. So first, about compression techniques. So there are a few compression techniques that we apply all over our file format implementation. So the first one is bit packing and variable int encoding, which are, so Michael Bush, if you remember his keynote from yesterday, described v-int encoding, where basically the first bit of a byte is a continuation bit, meaning that if it's 0, it means that you don't need to read other bytes after this one, and if it's 1, it means that you need to read at least another byte. These techniques are used for example, posting list and numeric doc values. There is also LZ4, which is used in version 4.1 in order to store stored fields. So This led to a dramatic reduction of the size of stored field, which made quite a few people happy, because it's very common that your stored field are going to take maybe like 70% of the size of your index. So this is something that you want to compress. And something else that we are using are FSTs. So these ones can only be stored in memory, but they are very efficiently compressed, because basically it's like a map that maps strings to anything, and allows for sharing prefixes and suffixes. We'll have an example a bit later. And FSTs are used, for example, for the memory doc values format that I was mentioning a bit earlier, but it's also used for the terms index. So now I'm going to try to explain what happens when you run a term query in Lucene. So let's say that we are going to run a term query, and the term we are interested in is Lucene. So first, you need to go through the terms index. So the terms index is stored in an FST that I was talking about in the previous slide. So this FST is in memory, and it only stores prefixes of the terms which are contained in your terms dictionary. So in an FST, you have a start node, which is the one on the left with an arrow pointing on it, and you have final nodes. So the final nodes are the one in dark green. And then in order to find the content of an FST, you need to go through the edges, which are called arcs, and an arcs has one label, which is a character, and one weight, which is 0 by default, and when there is a slash and a number, the number is the weight of the arc. So, for example, the first arc that you can see on the left means that the label of the arc is B, and it has a weight of 2. And when you go through the FST, you are going to sum up the weights of the arcs that you are visiting. So, for example, let's visit the upper part of the graph. So we are going through B, then R. We accumulated a weight of 2, and we are on the final node. This means that there is one entry in these FSTs whose key is BR and whose value is 2. If we keep going through the FST, we are going through A, which has a weight of 1, then C, and then we are again at the final node. This means that BAC is stored in this FST with a weight of 3, etc. You can do that for all the terms. And in the case of Lucene, we found a prefix for Lucene, which is Luc, the third entry of this FST, which is associated with 4, which is going to be the offset you will need to seek in your terms dictionary. So this is about the terms index. This is very memory efficient because it only stores prefixes. So it doesn't load a lot of things in memory, and it's very memory efficient. So getting back to our term query, we are searching for Lucene. We found that there are terms started with Luc, and we can find them at offset 4 of the terms dictionary. So let's go to the terms dictionary. So the terms dictionary is basically a sorted list of all the terms which exist in your index. So how is it stored? Because it is sorted, you are going to have consecutive terms which are going to share prefixes, and the terms dictionary is trying to take advantage of this for compression. So in this example, we have several terms which are Luca, Lucas, Lucene, Lucky, and lucrative. And since all these terms share the same prefix, the terms dictionary is going to add a flag in order to say that all the terms following this flag are suffixes, and the prefix is Luc. So based on the offset we found in the term index, we jumped on this block whose prefix is Luc, and we are going to go through every term. So first Luca, it doesn't match Lucene, we are not interested. Let's go to the next one. Lucas, we are not interested as well. Then Lucene, perfect. Is the term we were looking for. We can stop enumerating the terms of the term dictionary. We just found that Lucene is actually contained in the term dictionary. It has a frequency which is equal to 9, and it's stored at offset 205 in the posting list file. So now, let's go to the posting list file. So here are posting lists. So basically, posting lists are a sorted set of document IDs which identify the doc IDs that contain this term. So the way they are encoded is that Lucene is using a modified version of P4 delta encoding. So 4 stands for frame of reference. And the way to encode data with P4 delta is first, you need to delta encode your values. Then you are going to split your values into blocks into fixed size blocks, but in Lucene practice we are using 128. And then we are going to compute the number of bits which are required per delta in order to store the block. Finally, the number of doc IDs that we are storing in the posting list is not necessarily a multiple of 128. So what we do is that we keep the last values in the end and we store them using variable int encoding. So let's take an example. Here we have a posting list with a block size of 4, and we have 10 doc IDs. Doc IDs are stored using integers. This means that storing this posting list, if we didn't do any compression, it would take 40 bytes. So 10 doc IDs and 4 bytes per doc IDs. So let's try to compress them. So first, we are going to delta compress this list. This means that we are going to replace 3 with 3 minus 1, 4 with 4 minus 3, etc. Numbers are going to be much smaller, and this is very interesting for bit packing because the smaller the value, the fewer bits per value we are going to be able to use. Then we split this posting list into blocks of 4 values. So first we have 4 values which are 1, 2, 1, 2, 4 new values which are 2, 12, 2, 4, and in the end we didn't have enough values in order to form a full block, so we have 2 values that we are encoding with vint encoding. So how much space does it take? The first block needs 2 bits per value. There are 4 values, meaning 8 bits. So this is a single byte. The second block needs 4 bits per value, meaning 4 times 4, 16. This means 2 bytes. And finally, 4 and 1 require only 1 byte per value. So in the end, we are going to use 1 plus 2 plus 2 plus 2. This is only 5 bytes compared to the original 40 bytes that we needed to encode the posting list if we didn't do any compression. So this is how Lucene compresses posting list. And that's it. So we had to run term query, and we just found the doc IDs which are associated with the term Lucene. Now that we have the doc IDs, something that we are interested to get are the stored fields associated with these doc IDs. So how does it work? So stored fields are written into 2 files. One of them is called the stored field index, and the other one is called are the stored field data. So let's start with the data. So basically, we are going to store sequentially all field values in a single file. So this is this part of the graph. So basically, the numbers here are the doc IDs of the documents that you are storing in your stored field data files. So they are in order, as usual. And so we first have document 0, document 1, document 2, etc. The way the stored field format works is that when it has to ingest document, it first buffers them into memory. And once the memory buffer grows beyond 16 kilobytes, it's going to flush it on disk and compress it using LD4 compression, which is a very lightweight compression algorithm. And for example, in that case, the first block would be made of 3 documents, document 0, 1, and 2. Second block would be made of document 3. And the third block would be made of documents 4, 5, and 6. So that's it for the stored field data file. And this is, if you have a Lucene index, this is probably a file which is taking maybe 60 or 70% of the size of your index. But then we need to be able to look up field values in this file, meaning that we need to have an index. So the index is actually the part the doc IDs and the offsets, which are written a bit up on the graph for the stored field data. So what we are going to do is that for every starting block, we are going to store a doc ID and an offset. So the doc ID is the document ID of the first document which is stored in the block, and the offset in the stored field data file, where we can find the stored field for this first document of the block. And that's it. So we have a first block. The index value for the first block is doc ID equals 0, offset equals 42. For the second block, we have doc ID equals 3, offset equals 127. And for the third block, we have doc ID equals 4, and offset equal 199. So how do we search in this index? It's very simple. The only thing you need to do is to binary search based on the doc IDs. So for example, let's say that you are looking for document 2. So if you do a binary search over this index, you will find out that document 2 is stored in the block which is stored for doc ID 0, because doc ID 3 is already greater than the document you are interested in. So document 2 is stored in the first block. Then it is stored at offset 42. So you are going to go to offset 42. You are going to decompress the block. And then inside each block, there is a min index at the beginning, which tells you where data for a specific document starts. And this is how you get stored field information for a single document. So we need to binary search on the index. So this is not something we want to put on disk, because it's going to be there are going to be a lot of, otherwise there would be a lot of disk sticks, and this is something we don't want. This is why we store this index in memory. But usually it's very, very, very small. So one way to explain it would be, for example, we are storing only one index entry per 16 kilobytes block, and one index entry takes at most 4 bytes for the doc IDs. I mean, I'm considering that there is no compression at all on the index. So the doc ID is going to take 4 bytes because it's an integer, and the offset is a long, so it's going to take 8 bytes. So in the end, one index entry is only 12 bytes, and a block is 16 kilobytes. This means that even in the worst case, your index is going more than 1,000 times smaller than your stored field data. This means that if you have like a 1 terabyte index stored field in the worst case, I mean the index in the worst case is going to use 1 gigabyte of memory, but actually it's going to use much less because we are compressing these index entries. So if you notice, doc IDs are going to be in sorted order and offset as well, and we take advantage of that in order to compress it. So basically what we do is that we do a linear regression between doc IDs and offsets, and we rely on that in order to compress the stored field index. And also, in the worst case, it can take up to 12 bytes per index entry. In practice, it uses many fewer bytes. So I was talking about an index of 1 terabyte that could require 1 gigabyte of memory in order to store the index of the stored field. In practice, it is much less. So and that's it. So basically, with what I described, this shows you that getting a stored document in a Lucene index only require one disk stick, because the index is in memory, and so the only thing you need to do is to go to the offset, which is associated with the doc ID, when you find the block where your document is. So, as a conclusion of the query execution we just ran in order to search for Lucene in our index, so we had to do 2 disk sticks per field for search, and only 1 disk stick per document for stored fields. So this is how search in a Lucene index works. So this may look like a very high number of disk sticks, but most of the time you won't see actual disk stick happening, because it's very common that the terms dictionary in the posting list are small enough to fit into your file system cache. So as I said, most of the index size is usually taken by term vectors if you have term vectors, but if you don't have term vectors, most of the size of your index is going to be taken by stored fields. meaning that term dictionary and posting lists are very small and tend to fit into the file system cache. There is one very nice optimization that Lucene is applying so that you have less than 3D stick, even in the worst case. It is for terms which have a frequency which is precisely equal to 1. So this happens all the time if you have primary keys, because every term will be associated with a single document. So what it does in that case is that it's going to inline the posting list into the term dictionary. So if you remember the structure of the term dictionary, so what will happen here is that instead of storing frequency equal 1 and offset equals 101, it's going to store frequency equal 1 and doc ID, which is the only matching doc ID for this term, equals, for example, 42. So this means that for all your primary keys, Lucene is going to do only one disk stick in the worst case per field. Okay, so that's it about Lucene internals. Now I'm going to ask you a quiz. So it's unfair because I already know the answer, but let's try to do an experiment. We have a Lucene index, and we are computing the amount of query per second we are able to run on this index based on the number of documents in the index. So in order to make the problem simple, the index is fully static, and the number of segments is always equal to 1. So there is nothing that can happen that could be related to segment merge or something like that. The index is fully static and is always made on one segment. And if you compute the number of queries per second according to the number of documents in the index, you will see something like that. At the beginning, performance will degrade very gracefully, and then something weird will happen, and then performance will decrease a bit faster, and then something again very weird will happen, and performance will decrease even faster. So, do you have any idea why this happens? Yes? So, the answer which was given is the correct one, and the answer is that it's related to the size of your file system cache. So what is happening there is that 4.1, so at the beginning we had a very small index, but it grows, and in the end, the stored fields are going to be larger than the size of your file system cache. This means that stored field requests, which were always served through the file system cache, meaning in memory previously, are going to be translated into actual disk stick. And this is going to slow down your search. So as the index grows, more and more queries to the stored field API are going to be translated into disk stick. This is why performance decreases much faster. And we are going to hit a single point, which is 2, and something weird is happening again. So in that case, this is when the terms dictionary and the posting list are not fully in the file system cache, and then it's going worse and worse, and performance is going to decrease very quickly. So this is important to know because this has very important implications. So what are the implications? So first, you need to give free memory to your operating system. Let's say you have 24 gigabytes of memory. If you are giving 10 gigabytes of memory to your Lucene, Sora, or Elasticsearch process, there will only be 14 gigabytes available for your file system cache. This means that if your Lucene process actually needs only 5 gigabytes, you would be able to gain 5 gigabytes of file system cache, and this is something that would allow you to go from there to there, where performance would be much better. So another example is that let's imagine that you are really using as little memory as possible for your Lucene process, and you are in a sharded environment where you have maybe 5 shards, and you are right here. This means that if you had maybe 7 or 8 shards, your shard would be smaller. You would be able to be on this part of the graph, and your search would be much faster. So again, file system cache is something that people very often overlook, although it's it's probably performance factor number 1 for Lucene search. So this is something that you need to understand and you shouldn't play against the file system cache. You need to use it in order to make your queries fast. So you need to be aware of this. We are building search applications so that they are fast enough for your use case. Okay, and that's it for my presentation. I hope you enjoyed it, and if you have any questions, feel free to ask. So the question is, how do you compute how much space you need to give to your file system cache? So a recommendation I often give is that if you go to your index, there are a bunch of files in there, and just compute the sum. Compute first the size of your index, then you are going to subtract the sum of the sizes of the .fdt files, which is the extension which is used for stored field data, which is, as I said earlier, probably the biggest part of the index. If you want to be on that part of the graph, you need your file system cache to be at least the size of your index minus the sum of the sizes of your .fdt files. So this is at least, my recommendation is whenever possible to have at least this amount of memory for the file system cache. But if you don't care much about search performance, for example, if you are running search for, archive search, for example, where you have one query every 10 seconds, and people don't care if search returns in 2 seconds, there is definitely no problem with being in the last part of the graph. This is only really important if you want to be at the beginning of the graph. So maybe I can tell a story, actually. My first motivation to work on stored fields was because in my previous company, we had some indexes where we realized we were on that part of the graph. And we had when I say on that part, I don't mean here. We are right here. So these were already quite high-end machines that had 64 gigabytes of RAM. So the question is, how do you decide how long should be the prefixes that you store in your terms index? So I don't know the exact algorithm. The only thing I know is that it's adapted. So for example, let's say that you are indexing a lot of terms. But among these terms, there are a lot of URLs which are starting with http, / etc. Actually, the algorithm is intelligent enough in order to try to make, it's going to try to make each prefix map to as many values. So for example, if we were storing these terms with URL addresses, maybe we would have only a prefix for A, a prefix for B, then a prefix for maybe OA, OB, and for, IA, IB. And then when we would come to H, we'd store H, HT, HTTP, colon, / etc. It's very adaptive, and it tries to make every entry of the FST map to blocks which contains almost as many documents. So that the terms index is fair to the repartition of terms in our terms dictionary. Otherwise, if we only stored maybe up to a prefix length of 5, and if you were only storing URLs, actually the terms dictionary, the terms index wouldn't be useful at all because you would have a single entry, and all our URLs would match this entry, and then you would need to browse the whole terms dictionary in order to find matches, and this is not something that you want to happen. So we try to make the terms index smart enough to compute the prefix length based on the number of matching terms. Okay, so if there is no more questions, I'd like to thank you all for attending this session, and well, safe flight home. Yeah. Thanks.